Hello and welcome to day 14 of Advent of Code, part 2. We've got a slight change here to what we did in the first video where we had the run mask. We've actually got a slightly different set of rules for how the mask will actually work now. If the bit mask bit is 0, the corresponding memory address bit is unchanged. If the bit mask bit is 1, then the corresponding memory address bit is overwritten with 1. And if the bit mask bit is X, the corresponding memory address bit is floating. A floating bit is not connected to anything and instead fluctuates unpredictably. In practice, this means the floating bit will take on all possible values, so it's either a 0 or a 1, or is it both a 1 and a 0 at the same time until you find out which one it is, potentially causing many memory addresses to be written all at once. So let's take this. We're going to use this as the example here in our input here in a moment. Right there. So we'll use this as the example for part 2, for our part 2 function. But let's walk through it. So we have our mask, which has zeros and x's and 0, 1, x, right? And we have the zeros. Our value is 100. Then we have a mask, a new mask, and then we have a memory. Okay. So we have an address. Address is this is the decimal representation of 42. Here's our mask, and we have this result. X ends up being any particular value. It could be a 1, it could be a 0. So after applying the mask, 4 bits are overwritten, 3 of which are different, and 2 of which are considered floating. They're X bits. Floating bits take on every possible combination of values. With 2 floating bits, 4 actual memory addresses are written. So we end up with 4 different values being written into memory. Next, the program is about to write to memory address 26 with a different bit mask. So we were given a separate bit mask, and here's memory address 26 with that particular value, 1, not bad. Here is our new value. Here's our mask, and the result is that. This results in an address with 3 floating bits, causing writes to 8 memory addresses, right? 2 to the third, right? This was 2 to the second. The entire 36-bit address space still begins with initialized with the value 0. The sum is 208. Execute the initialization program using an emulator for a version 2 decoder chip. What is the sum of all values left in memory after it completes? Okay. So we actually need to make a slight change to our original code here. Part 1 will actually look relatively similar to part 2, except that we will no longer have this run mask. This whole line is not going to be relevant at all. We still process the mask the same way, we still split the operation and the argument, but now we actually need to come up with a different way of solving this particular piece. So at this point, we're going to create a new function that we're going to call run masks, and this is going to basically handle the new logic of this, and we will have something that's essentially for m in run mask with the memory position and our given mask. This is going to give us an output that we can then reference as something along the lines of memory m is going to now equal our int arg. Okay, but we need to get argument. So, but we now need to identify all of those different memory locations. from the memory position. Excuse me. Okay, so we're going to have run masks. Okay, so we already had one run mask, and now we have run masks. Yay! That's fun, right? So we're going to have a memory position, and we're going to have our mask. And we're going to say if not mask, or basically if mask is empty, we're going to yield 0. And yes, we are outputting a generator here. Yeah, we're essentially going to have a generator value here that we can iterate through here. So otherwise, and this is where we're going to have some recursion going on, for m in run masks, memory position divided by 2, right? Because we're taking half of the memory positions, half rounded down, for mask all the way up through the last value. So we're essentially going to go through and rerun the masks and go from the start all the way to the end, and we're going to cut off all of the different pieces, and we're going to have X, and we're going to process zeros, ones, and X's slightly differently depending on what that very last value is there. Another way of doing this is you could simply take mask and then swap everything and then iterate from the beginning. I'm going to iterate from the end in this case. So if mask minus the last value of mask is 0, then we're going to say yield 2 times m plus memory position modulo 2. Otherwise, if it equals a 1, two times m plus 1, then this is going to be, we're going to yield 2 different values here, right? We're gonna yield 2 times m, and then we're also going to yield 2 times m plus 1. Since we have these yields, we don't actually have to have a return function, a return keyword statement. So essentially, we iterate through each of the values that are yielded, and that we reassign the new value of memory using that particular argument. So that value argument right there. Okay. So it essentially looks very similar, except that we have now, instead of run mask, we have run masks. Oh, run masks. There we go. So Python day 14 208. Let's double check that this in fact is correct. The correct answer is 208. So we can jump back over to our input and use that. There we go. So that should be the correct answer. And there it is. Okay, so there we go. So yeah, with all of that being said, I know that this is yeah. So with all of that, hope this was useful, enjoyable. This was one of the less interesting Advent of codes to me personally, but still fun to go through. If you have any questions or comments, throw those below the video. Happy to respond there. If you do like the video, remember, like, share, subscribe, and otherwise I'll just see you in the next video, day 15.